Hello class, this is CSE-4600, Section 1, Week 14, Spring 2025. Before we continue our discussion on deadlocks, deadlock avoidance, and deadlock prevention, let's go back and answer the questions related to file systems. Number 1. Systems that support sequential files also have a rewind option. Is a rewind operation necessary for systems that support random access? The answer is no. It's not necessary to have a rewind option. The reason why we have a rewind option is because back then, files and data were stored on tape reels, and you had to physically rewind and fast forward the tape to get the read-write head to a specific position to read something from the tape. With hard disk drives and also solid state drives, there's nothing to rewind. We have random access, which means any one byte on the disk can be easily accessed as any other byte. So with every byte easily accessible, we don't need a rewind option. We don't need to move anything to a specific position. Well, with the hard disk drive, there is a spinning thing, but don't worry about that for now. With random access, because we can access any byte as easily as any other byte, because every byte is easily accessible, we don't need a rewind option. But if you do want a rewind option, just access the first byte of the file. So that's number 1. Number 2, suppose a system only had one directory, so you can't make subdirectories, but allowed for arbitrarily long file names. Can you still organize files in a hierarchical way? The answer is yes. So, every file on your system has a path name that secretly comes before every file name. So, these are for 4600, so these are all your files for the class. So secretly there is a path name that comes before every file, and the path name is actually up here. So if I click the address bar, that's the path for this folder that contains all these files. If we had a system that did not allow for subfolders to be made, the way we would organize them is pretend you can take this path name and add it to the beginning, prepend it to every file name. Now, every file name is absurdly long. It starts with user slash whatever slash such and such CSE-4600 underscore 1730 1845 TR CGI 110 slash, say, 4600 underscore chapter underscore 3 underscore part underscore 3.tbtx. So, how we would organize files on a system that did not support subfolders but allowed for arbitrarily long file names? We take the would-be path name and add it to the beginning of our file name. Now, all of our files have insanely long file names, but they are organized. Is this a good organization system? I'll let you think about how good this organization system is. But think about how easy it would be to move folders around, and then think about how easy it would be to move folders in such a system. Is this system easy to work with? I'll let you answer that one. Number 3. Some systems provide a separate rename operation to rename files. How is it different from create a new file with a new name, copy the contents of the old file to the new file, and then delete the old file? Well, for starters, you gotta do all those steps. You gotta create a new file. That means you have to make a new directory entry for a new file. Then you gotta copy the contents of the old file to the new file. So it means you have to read the old file and then write the contents to the new file. That means as this file grows, you gotta allocate new blocks of space for that file. And then you gotta delete the old file, which means removing the directory entry for the old file. Now, when we delete a file, it's not the same as, say, bulldozing a building. Deleting a file and bulldozing, if you think about deleting a file as bulldozing a building, it isn't. It would be more like if you demolished the driveway up to the building and calling it good. That's what it's like for files to be deleted on a computer system. The files, the bytes themselves, aren't scrubbed and reset to 0. Rather, they're left there to be overwritten by new files. Which means when we demolish that driveway to a building, sometime later it could be like half the building is gone and then new development is right next to it. It's free real estate, so with a rename operation, if you want to rename a file, just go to that file's directory entry and change the name. Update the name field for it. That's it. If you want to go with these steps of create and then delete, you need to create a new file. You gotta copy the old file to the new file. You gotta allocate space for the new file, and then you have to deallocate the space that was used by the old file. Additionally, suppose the old file was made like in January 2021, and you made the new file in like May 2025. Is it May already? The problem is now, if you copy the old file's contents to the new file, then the metadata, or the file attributes, will only reflect when the file was made, which was May 2025. It won't say it was made in January 2021. So, if you go through the steps of renaming a file, you preserve all the other metadata that was associated with the file. If you create a new file, copy, and then delete the old file, now you have a new file with completely different metadata. That's the other difference with renaming and create then delete. So that's the answer to that question. The final question is, contiguous allocation leads to fragmentation since the last block of a file isn't always completely full, leading to wasted space. So how I worded this will lead you to come to the conclusion that the problem is internal fragmentation, which is true because the last block in contiguous allocation, the last block of a file will not always be full. If, for example, a disk had 1024 byte blocks, and we have a file that's 4097 bytes, we need 5 blocks. So the first 4 blocks will be completely full with 1024 bytes each, and the 5th block will only have 1 byte. So that means the other 1023 bytes of the last block are wasted space. That is internal fragmentation. So how I worded this, and I guess this is an error on my part, I may have led you to believe that internal fragmentation was the only issue, when it's actually both. But more to the point, it's also external fragmentation, because we are allocating files in contiguous blocks, meaning we cannot have the file be in blocks scattered across the disk. We can't have like blocks 1, 2, 3, and then 6, 7, 8, and then 13, 19, 15, 16. Not like that. If we have a file, it must start in one location and then go consecutive blocks to the last block. What this also means as files are created and deleted, they're gonna leave behind holes of their own, which may not necessarily be large enough for new files. This is external fragmentation. And the solution to external fragmentation is You may have heard of it as disk defragmentation, but the term used in the textbook is compaction. That's where we take all the files on a disk, move them to one location, which necessarily means that all the free space moves to the other end of the disk and becomes one huge contiguous block of unused space. So technically the answer is both. If you only put one of the or the other, I'll still take it, but technically the answer is both. If you just put down one of the other or the other, I'll still take it, even though I am grading this assignment based on completion rather than correctness. So that's the answer to the last question here. Alright, let's begin looking at your next material. So this is part 3 in our discussion on deadlocks and how to deal with deadlocks. There were 4 strategies, and we looked at 2 of them so far. The first one was ignore the problem. That's called the ostrich algorithm. The second strategy is detect that there is a problem and do something about it. So as I had rambled on in the last video, these 4 strategies sound like upgrades. So the first strategy is to pretend the problem doesn't exist. The second strategy is to acknowledge that there is a problem and do something about it. Now the third and fourth ones are like this. The third strategy is called deadlock avoidance. It means we look ahead and see whether we are heading straight towards the problem, but we do measures to steer away from the problem. The fourth one is to keep the problem from happening in the first place. So we're going to look at deadlock avoidance. In our discussion, we assumed that when a process requests for resources, it requests for all of them all at once. The problem with that is, in most systems, processes request for resources one at a time. They make one request at a time. They don't make one big request saying, I need all of these resources all at once. No, they make one request, realize they need more, and then they make another request. So the question arises, is there an algorithm that can avoid deadlock by making the right choice each time? The answer is yes. We're going to begin our discussion on what is called a resource trajectory. So imagine this. So this graph represents what is called a resource trajectory. Horizontal movement is progress for process A. Vertical movement is progress on process B. We can only move right and we can only move up. Diagonal movements are not allowed because we're assuming we only have one CPU core to go around. That means we can only run one CPU at a time. So we move in this zigzag. At some point, one process needs the printer and then the plotter. That's for process A. At some point in the execution of process B, it's going to need the plotter, and then it's going to need the printer. So, if we just move straight to the right, that is process A making progress from start to finish. If we just move along the vertical axis going straight up, that is process B making progress from start to finish. It's going to use the plotter and then the printer. Meanwhile, process A needs to use the printer and then the plotter. But we need both processes to run to completion. That's this point here where both processes have finished. So we need to make some path from the start all the way to the end. But the rule is we can only move horizontally and vertically. We also cannot move backwards because that is making negative progress. We're traveling back in time, basically. So what this is developing an intuition for what is called a safe state. Look at the regions for which process A is using a printer. And then look at the region for which process B is using a printer. So process A uses a printer at times I1 to I3. Process B needs a printer at times I6 to I8. That means we can draw out this shaded region where processes A and B are using the printer, which is actually impossible because we only have one printer. We're assuming you only have one printer and one plotter in this case. If we had two of each resource, then both processes can run at the same time, or rather the CPU context switch between both of them, and we would not have an issue. But we're assuming we only have one of each resource here. So the shaded region represents where the two processes are using the same resource at the same time, which is impossible. Similarly with this other shaded region, bounded by I2 and I4, and also I5 and I7. So this region here, that is where both processes are using the plotter at the same time, which is also impossible. So what does this mean for our trajectory? It means we cannot enter those shaded regions. So we have these two regions which are impossible to enter. Is it okay if we is it okay to traverse the boundary of these regions? Yes, it is. So if we're riding the boundary of these regions, as long as we never enter the region, we're okay. That means if we're at point T and we go to the right, that means process A is using the printer and now it's using the plotter. At the same time, process B is about to use the plotter, but it isn't because, well, we didn't progress with process B's progress yet. So if the moment we move up, that means, okay, if we're at point T, the moment we move up, that means process B is using the plotter. The moment we keep going right from T, process A is going to use the plotter. So with these rules, the goal is to find some path that starts at a beginning, P, and ends at U. That's the finish line where both processes finish. So again, these shaded regions represent areas where both processes are using the same resource at the same time, which is impossible. And once again, we can only move up and right. We cannot backtrack. So if we are at point T, what is our next move? Well, we can only move up and right, right? So at point T, it would sound like either move up or right would be valid moves. But here's a problem. If we move up from point T this way, you see my cursor? If we move up, we hit the boundary that leads into this impossible area, and we cannot enter the impossible area. So the moment we hit this boundary, our only option is to move right. But then we hit this boundary of the other impossible region. That means there is some point where we would get stuck. And this point that I'm having the cursor over, that is deadlock. So this point here, that is deadlock. And here's what's going on. There are regions in this area that are totally safe. We can move through those regions without any issue. There are some regions that are impossible to enter because they suggest impossible conditions. Processes A and B using the same resource at the same time, which is not allowed. There are some movements we cannot do because that would be moving back in time. So given the rules of the game and the only legal moves, there are some areas where if we move into them, we get stuck, and the only outcome left is deadlock. So this shaded region I have here in red, which is bounded by I1, I2, I5, and I6, that's an unsafe region. So this is a region where once you enter this unsafe area here, the only outcome left is deadlock. So what does this mean for resource allocation? Well, suppose we're at point T right now. That means process A is using the printer. Process B has not used any resource yet. If we keep going to the right, that means process A, which has the printer, is gonna next get the plotter. If we move up, that means process B is gonna get the plotter, but it means process B needs the printer next. But process A already has the printer, and process A also needs the plotter next. But if we're in this region, it means process A has the plotter. No, process A has the printer, process B has the plotter, and then processes A and B need each other's resources. Deadlock. Within this region, process A has the printer and process B has the plotter. The next step in both processes' execution is to need each other's resources. But given the rules of our game here, we can only move up and right. We cannot backtrack. Which means the moment we enter this red region, our only outcome left is deadlock. It means in this scenario, for us to avoid deadlock, we have to turn right and then up. That means process A is going to use the printer and then the plotter, while process B waits its turn to use the plotter and then the printer. So this is what it means here. It means from P to Q, process A runs. From Q to R, process B runs. From R to S, process A runs and gets the printer. From S to T, process B runs and is about to get the plotter. But the moment we enter this red region, we enter an unsafe state that's going to lead to deadlock. So we cannot enter the red region because we would get stuck. So we go, take this purple arrow. That means process B waits its turn for the plotter. Process A gets the plotter next. And once we have cleared I4, it means process A will now have released both resources, and process B can get them next. At this point, process A will have finished, and we let process B do its thing, grab the resources, run, release the resources, done. So this is the intuition behind a safe state. In this abstract space that represents processes running, think of it as this abstract obstacle course where you can only do certain movements and some of them can get you stuck. The key is to find out which of those regions will lead you to getting stuck and avoid them. That is the idea behind deadlock avoidance. And that red region is what is called an unsafe state. So, our deadlock avoidance algorithm is based on the information from that diagram, and here we go. At any time during the system, there is a current system state consisting of the following data structures: E, A, C, and R, where E is the existing resources, A is the available resources, C is the currently allocated resources, and R is the requested resources, which sounds like our detection algorithm from before, our deadlock detection algorithm from before. Here's the definition of a safe state. A state is safe if there is some scheduling order in which every process can run to completion, even if all of them suddenly request their maximum number of resources immediately. So, we begin with a system with only one resource type. We have processes A, B, and C, which each has 3, 2, and 2 resources. We also know that processes A, B, and C need a maximum of 9, 4, and 7 resources, and there are only 3 resources left. So, through basic addition, if we add everything in the has column and add the 3 here, we know we have 10 resources in existence. So here's the thing. Each process has a known maximum resource need. But the thing is, not every process will ask for the maximum resource need right away. Process A asked for 3 resources, but it might need 6 more resources because its maximum is 9. Or it's possible that it might only needed the 3 resources and not ask for any more. So, if the other processes needed more resources, could we just willy-nilly give the 3 resources to B and C? Not necessarily, because what if process A needed more resources? The key here is to make sure that every state we're at is a safe state. So we can do some basic math to determine how much more of each resource each process needs. So if we subtract the max column from the has column, we know that process A may need 6 more resources. Process B may need 2 more resources. Process C may need 5 more resources. So, with that, how do we know that state A here is safe? Well, let's assume that every process suddenly requested its maximum number of resources. So process A asks for 6 more resources. Process B asks for 2 more resources. Process C asks for 5 more resources. And we are currently at state A here. Is there a process request that we can fulfill? Process A needs 6 more resources. Process B needs 2 more resources. Process C needs 5 more resources. And we only have 3 resources free. Is there a request that we can fulfill? Yes, there is. It's the request of process B. So we can give process B 2 of our resources, and we only have 1 resource left. Are we deadlocked yet? No, because process B has its request fulfilled, and then eventually it's going to release all of its resources and give them back, and now those resources are free again. Now we have to answer the same question again. Process A needs 6 more resources. Process C needs 5 more resources. Oh hey, we have 5 resources here. So we can just give those resources to C. It's going to use them, and then it's going to give them back. And now, after that, we would have 7 resources available. Process A needs 6 more resources. We can just give 6 of our resources to A, and then get them back, and then all 3 processes will have terminated. That means state A here is a safe state. Not once have we ever given any resources to any process. What we did is simulate it. So we did this sort of simulation to check whether every process will terminate. So here's the thing. We are in a safe state. If a process makes a request for resources, we run this simulation to see whether these processes will safely terminate afterwards. If we find a sequence of steps that leads to every process finishing, then we can say that state A over here is safe. So every time we have a process make a request, we check whether that next state would be safe. If it is, we grant that request. If it is not, we reject that request. So let's see what would happen if instead we had an unsafe state. So this is state B over here. What if process A requested an extra resource? Should we? So, if process A wanted if process A requested one more resource, then we can do some math to determine how much more of each resource each process needs. So we're gonna pretend to give one resource to process A and then simulate what happens next. So process A has 4 resources. The other 2 processes have 2 each. That means process A needs 5 more resources. Process B needs 2 more resources. Process C needs 5 more resources. We know that process B needs 2 more resources. We have 2 more resources. We can let process B get those 2 resources, and then eventually it'll run and then give them back. That means next we have 4 resources available in state D. But process A still needs 5 more resources, and process B has terminated, and process C needs 5 more resources. But we only have 4 resources. We don't have enough! That means this state B, is unsafe. So if process A requested 1 more resource, it will lead to state D, which is a deadlock state. That means state B is unsafe. State B is reached when we give process A 1 resource. That means, but we have shown that once we go to state B, we end up at state D, which is a deadlock state. That means state B is an unsafe state. That means if process A asks for 1 more resource, just 1 more resource, we're gonna end up in an unsafe state and your only outcome is deadlock. So that means reject process A's request for 1 resource. Also, note that I say that an unsafe state will lead to a deadlock state. Not always. So here's a little bit of nuance. An unsafe state is not a deadlock state, but it's not guaranteed to lead to deadlock, nor is it guaranteed to go back to a safe state. It's possible that a process may finish without requesting additional resources, or it might end up releasing one. Each process may need more resources than it was allocated, but maybe not. The thing is, it is not guaranteed that each process will ask for more resources or not. That means with an unsafe state, it's not guaranteed that every process will finish. Which conversely means it's not guaranteed that we'll end up in deadlock. So we gotta assume the worst with an unsafe state. Therefore, we need to avoid the unsafe state. Basically, it sounds like our deadlock avoidance algorithm is the same as our deadlock detection algorithm, and it does, but with one key difference. When a process requests a resource, we don't fulfill it right away. Rather, we simulate what happens if it's fulfilled, and then grant it if there's no deadlock. We grant the request if it does not lead to deadlock, or reject if it does lead to deadlock. More specifically, if we grant the request and the next state is an unsafe state, reject the request. If the next state is a safe state, grant the request. So this leads into what is called the banker's algorithm, which is based on how a bank would loan out money only if it would be repaid. This algorithm checks whether fulfilling a request for resources leads to an unsafe state. If so, reject the request. If not, grant the request. So here's another example where we have 4 processes. Initially, they have 0 resources allocated to them. But we know how much of each resource each process needs. 6, 5, 4, and 7. Sometime later, those processes will have asked for resources. So process A has 1 resource, process B has 1 resource, process C has 2 resources, and process D has 4 resources. Remember, not every process will need that many resources right away, and each process will have requested fewer resources than its maximum. It might ask for more, but it's also possible that it might not ask for any more. But we need to assume that they're gonna ask for more. Is this a safe state? Is this a safe state? To answer the question, let's do some math. We subtract max from has, and then we can add this request column. So that means process A might ask for 5 more resources. Process B might ask for 4 more resources. Process B might ask for 2 more. Process D might ask for 3 more. But we're going to assume that every process is going to request for these quantities. So we're going to assume that process A needs 5 more resources. Process B needs 4 more. Process C needs 2 more. Process D needs 3 more. There are 2 resources left. Can we fulfill one of these requests? Yes, we can. That is going to be the request of process C. So in the simulation, process C is going to have 4 resources allocated to it, and then eventually it's going to free them up, and now we have 4 resources available. Now we have 4 resources available and 3 more requests left. We check process C because that one ran to completion. Is there a request that we can fulfill? Turns out there are 2 of them. If you have more than one process whose request can be fulfilled, just pick one. We're going to pick process D for our purposes. So let's just say process D is next. So when process D, once we know that process D's request can be fulfilled, what we're going to do is we're going to speed this up, and we're going to take the processes and the resources that process D has and just add them back to the free pool here. And then we put a check mark to denote that process D has terminated. Now we have 8 resources left, and processes A and B need 5 and more resources. Either one could be fulfilled, but let's pick process A next. So process A only has 1 resource allocated to it, so we're just gonna take that 1 resource it has, put it back in the free pool here, so now we have 9 resources available, and we can check off process A as running to completion. Now we have 1 process left, and that's process B. Process B needs 4 more resources. We have plenty, and yeah. We check off process B, and now we know that process B has terminated. All 4 processes have terminated. That means we were in a safe state. So if suddenly every process requested its maximum amount of resources, and we only have 2 resources left, we can fulfill every process's request. And if we can fulfill every process's request, we know we are in a safe state. Let's go back to state B. We know this state is safe. Let's say process B makes a request for 1 resource. Without granting it right away, let's simulate what would happen if we granted it. So, process B only had 1 resource allocated to it. We're going to enter this new state, but not yet. We're going to see whether state C is safe. So process B has 2 resources allocated to it. We can determine what each process's request is. Process A needs 5 resources. Process B needs 3 resources. Process C needs 2 resources. Process D needs 3 resources. But we only have 1 free resource available. We can't fulfill any of these. That means process C is an unsafe state. That means by granting process B its request for 1 more resource, we enter an unsafe state. It's not guaranteed that this will lead to deadlock, but it's not guaranteed either that this will lead to another safe state. Assume the worst. Therefore, this is an unsafe state. Do not enter. Do not grant process B's request. Also, the Banker's algorithm works for multiple resource types. So we have matrices C on the left and R on the right. We also have vectors E and A, but also a third one called P. that is the number of resources currently allocated to processes. That is what you get when you sum the columns of the left matrix here, which, as I said, that is matrix C. So if you add all the columns in this matrix, you get vector P. So this is the algorithm for determining whether a state is safe. Look for a row in R whose unmet resource needs are less than or equal to A. If no such row exists, then the system will eventually deadlock, assuming all processes keep the resources until the exit. If more than one process is eligible, just pick one. It doesn't matter. Number 2, assume the process of the chosen row requests all the resources it needs and finishes. Mark that process as terminated and add all of its resources to vector A. Number 3, repeat steps 1 and 2 until either all processes are marked as terminated, even that means the current state is safe, or no processes are left, or no process is left whose resource needs can be met, meaning the current state is unsafe. Let's try it out. I'll leave it as an exercise to you to verify that this state is safe, but it is. This state is safe. But let's say process B makes a request for the printer. Is this a safe state? So, this is the current state, and this is the state of the system if we grant process B the request for a printer. That means we previously had 2 printers available, now there's only 1 printer left. It also means we only have 1 tape drive and only 1 printer left. Can we fulfill the next? Is there a process whose request can be fulfilled next? Remember, we only have 1 tape drive and only 1 printer left. Process A, B, C, D, and E still have outstanding requests. Is there a process whose request can be fulfilled? Yes, there is. It's actually process D. So process D only needed 1 printer. So that means we know that process D's request can be completed. That means we can just mark process D as terminated and then add all of its resources back to A. So we cross out. So process D has 1 tape drive, 1 plotter, and 1 Blu-ray drive allocated to it. We're gonna take all those resources and add them back to vector A. So now we have 2, 1, 1, and 1 resource available. Is there a request now that can be fulfilled? There are actually 2 of them. Process A and E their requests can be fulfilled next because look, they only need 1 tape drive and 1 plotter, but process E needs 2, 1, and 1. Those are less than or equal to 2, 1, 1, 1. So 1, 1, 0, 0 and 2, 1, 1, 1 are both less than or equal to A. That means we can either fulfill process A or process E's request. Let's pick process E. So process E has 0 resources allocated to it. So when we add all of its resources back to A, nothing changes. But that also means that we have 2, 1, 1, and 1 resource available, which we know was already enough to fulfill process A. So let's just go ahead and check process A, mark that as terminated. So now we have processes B and C left. Is there a process whose request can be fulfilled? Turns out both of them can be fulfilled, but we can only fulfill 1 at a time. Let's pick process C. So process C, we can mark that as completed, and we can add its resources back to vector A. So the last step is to see whether process B's request can be fulfilled. And yes, it can. So now that process B has been marked as terminated, every process has been marked as terminated. That means if we grant process B a request for the printer, this becomes our next state, but we have verified that this is a safe state. Therefore, we can grant process B's request for the printer. There are some issues with the Banker's algorithm. So ever since Edgar Dijkstra first published the Banker's algorithm back in 1965, it has been since described in nearly every OS book out there. Though the author points out one issue that he states is overlooked by most other authors, and that is processes don't know in advance how much their maximum resource needs will be. Additionally, the amount of resources available on a system can change as users log in and out, and if hardware resources break. So if a printer breaks in the middle of if a printer breaks down in the middle of processes running, then suddenly you just lost one resource that could lead to deadlock, potentially. Or maybe not, because someone might have an extra printer available and just plug it in while the system's running. So the thing is this. Few systems can truly implement the banker's algorithm. The closest thing is a heuristic that approximates the behavior of the banker's algorithm. So that is the key issue with the banker's algorithm. Processes don't know in advance what their maximum resource needs will be. And the amount of resources available in a computer system can change when you account for users logging in and out and hardware breaking down. So, given the issues of deadlock avoidance, is there anything we can do about the 4 conditions for deadlock? Remember, there are 4 conditions needed for deadlock to occur: mutual exclusion, hold and wait, no preemption, and circular wait. So, we tried to steer clear of unsafe states that may or may not lead to deadlock, but the problem with that is we need a crystal ball. We need to look into the future to know how much of each resource each process will need, but each process don't know. Each process doesn't know how much they'll need. So, can we do better? Can we keep deadlock from happening? To do that, we need to negate one of the conditions for deadlock. Which one? We can try to attack the mutual exclusion condition, but there's a problem with that. We can't. If more than one process can use the printer, then the output would be chaotic. So, no, we cannot do anything about the mutual exclusion condition. There's one thing we can do, and that is don't assign resources to processes unless absolutely necessary, and make sure that as few processes as possible try to claim it. So there's nothing we can do on the mutual exclusion front. If 2 processes try to edit the same file, we might get garbled up results happening. And you can see this for yourself if you're ever gonna take CSE-5250 in the future. Can we attack the hold and wait condition? If processes requested everything they need all in one go, then we would not have deadlock. Can we do that? Also no, because processes don't know how many resources they need in advance. If we did know that information, we can use the banker's algorithm. Additionally, having processes request everything in advance would also be an inefficient use of resources. Say a process needs a printer and a tape drive. It needs a tape drive to access a file. But if it took 1 hour, if that process requested the tape drive and the printer, and it held onto them, but the process took 1 hour to search the tape drive for what it's looking for, then the printer will have been idle for 1 hour when it could have been used for something else. We just held up the printer for 1 hour for nothing. There's another way to break the hold and wait condition. When a process requests a resource, it temporarily releases all the resources it's holding, and then it tries to re-request them all at once. So that is another way of attacking the hold and wait condition, but for our purposes, we cannot do anything about the hold and wait condition. Can we do anything about the no preemption condition? If resources can be preempted, then we wouldn't have deadlock in the first place. Can we do anything about that? Also no. The problem is, a process may be in the middle of doing something with the resource. If you preempt a printer, while a process was using it to print something out, then congratulations, you have an incomplete printout. If you preempt a file when a process was in the middle of writing stuff to it, then congratulations, you just have corrupted data. In the case of the printer, we can handle that by spooling files instead. That is, the files are saved to the disk, and then a background process called a printer daemon comes in and sends those files to the printer when they're ready. This also eliminates deadlock over the printer, but it also introduces deadlock over disk space, which can be resolved by having lots of disk space. We can also virtualize resources, but not all resources can be virtualized. So that leaves one final condition, and that is the circular weight condition. And yes, there is something we can do about the circular weight condition. And the simplest way to do this is to have processes request resources in a specific order. Put another way, have processes request for resources in the same order. So if two different processes need a printer and a tape drive, have both of them ask for the printer and then the tape drive. Do not have one process ask for the printer and the other one ask for the tape drive, and then tape drive printer. Have processes ask for resources in the same order. If one process asks for the printer and then the tape drive, and the other one asks for the tape drive and the printer, both processes get their first resources, but then they deadlock when they ask for their second resource. An alternative is to assign a numeric ID to every resource, and then enforce the following rule. Processes must request resources in numerical order, such as by increasing resource ID. If one process acquires the first resource first, then any other process will have to wait their turn. Additionally, they can't request for any more resources until that previous request is fulfilled. So by forcing processes to ask for resources in a specific order, we eliminate deadlock. And that's how we eliminate the circular weight condition. And the simplest way to do that is to have processes ask for resources in a specific order, or to enumerate, or to give a numeric ID to every resource and force processes to ask for resources by increasing resource ID. And here's the proof for that. Suppose we have processes P1, P2, and P3, and resources R1, R2, and R3. They're all deadlocked. They're all in a circular weight, and they're therefore deadlocked. P1 is requesting R1, R1 is held by P2, P2 is asking for R2, R2 is held by P3, so on and so forth. Each resource is given a numeric ID, and we use a function, f of Ri, to give the numeric ID of a resource. This also means that if each process must be requesting processes in numeric order, it means that f of R1 must be less than f of R2. F of R2 must be less than f of R3. F of R3 should be less than f of R1. What this means is the ID of R1 should be less than the ID of R2. The ID of R2 should be less than the ID of R3, and the ID of R3 should be less than the ID of R1. But by the transitive property, if the first ID is less than the second ID, and the second ID is less than the third ID, and the third ID is less than the first ID, that means the first ID should be less than the first ID, and the second ID should be less than the second ID, and the third ID should be less than the third ID. So how can an ID be less than itself? It can't. What we have here is a proof by contradiction. We assume something is true, find a contradicting statement, and if we get a contradicting statement, that means what we assumed to be true was false to begin with. That means we don't have deadlock in this case. We don't have a circular weight. We therefore do not have deadlock. And this works for any number of resources and any number of processes. The only tricky thing is it might be difficult to enumerate every single process. So here's a summary of all of our approaches to preventing deadlock. For mutual exclusion, spool everything. For hold and wait, request all resources initially. No preemption, take resources away. And circular wait, which is probably the best way to prevent deadlock entirely. Order resources numerically, or have resources be requested in a specific order. There are a few other issues, and we're gonna look at these real quick here. Deadlock prevention and avoidance may not be viable in the general case, but they do work in specific applications, such as databases. A common operation in databases is for a process to request blocks for several records and then update them all at once. When there are multiple processes involved, then there is a danger for deadlock. This is called two-phase locking. In the first phase, the process tries to lock all the records it needs, one at a time. No changes are made. If the first phase is successful, it performs the second phase of updating all the records and then unlocking all of them. If a process fails at performing the first phase, such as if another process has locked one of the records it needs, then releases all of the locks it had acquired and starts over. Which sounds like we were negating the hold and wait condition, where processes request everything they need in one go. So this works for database systems, but it doesn't work for real-time systems, because in real-time systems, it's unacceptable for a process to terminate a job partway and start over. So far, we have talked about resource deadlocks, but there is another type of deadlock called a communication deadlock. Prevention of this type of deadlock is done by timeouts. When a message is sent from one process to another, a timer starts. If a timer goes off before the reply arrives, then the process resends the message. Sometimes, that message wasn't lost, but was instead delayed. In that case, the recipient may end up receiving the same message multiple times, such as add $1,000 to this customer's bank account. If we sent that twice under the assumption that the first one was lost, but was actually delayed, then oops, someone got doubly charged. The protocol, that's the set of communication rules, must be designed to prevent this from happening, and designing the protocol, that is a complex subject that is itself outside the scope of operating systems. There is another thing that can happen called live lock. Sometimes processes try to be polite to one another by giving up a lock so that a process can use that resource. But sometimes it goes too far, with processes basically saying, no you first, no you first, no you first, no you first. Processes aren't deadlocked, but they're not making progress either. It's called live lock. You might see this in real life too. So this is just a random screenshot from like a YouTube video for which car has the right of way. And then someone in the comments say, it becomes a standoff of people going, no you first, no you first, no you first. And no one gets anywhere. That is live lock. And then there's another thing called starvation. In a dynamic system, requests for resources happen all the time, and a policy is used to decide on who gets which resource when. Sometimes this leads to processes never getting the service they need, even though they're not deadlocked. This is starvation. When a process asks for a resource, and it never gets the resource. That's called starvation. And there are a few ways to prevent starvation. One is to use a first come first serve allocation policy, or give or increase priority for processes that have waited a long time. Have you ever been in a wait list for a class and you got a notification that says your priority in the wait list has increased? That is a starvation prevention technique, where over time you increase the priority of a process so that eventually its priority will be so high it gets the resource next. No, not everyone makes a distinction between starvation and deadlock because both don't make any forward progress. Others do make the distinction. A process can try something n times and try something else if all n attempts have failed, but a blocked process has no choice. So this is starvation. So with deadlock, processes don't get what they need, but with starvation, yeah, it's a little bit nuanced, and even I'm trying to and even I'm trying to find, even I'm trying my best and failing at articulating the difference between starvation and deadlock. So, a process can try something n times and try something else if all n attempts have failed. Block processes have no choice. So that's the end of our discussion on deadlock. Let's look at your next assignment, and this assignment is going to be an extra credit assignment. Let me show you what the questions are. Alright, so these are your deadlock questions. Question 1. Can you come up with a deadlock example from politics? Deadlocks happen all the time in like Congress or something. And just come up with an example of deadlock from politics. My point is, deadlocks happen all the time, and they're not always within the context of operating systems. Number 2. Can a resource deadlock happen with multiple units of one resource type and one unit of another resource type? Number 3. This is actually 2 questions that are combined into one, so it's valued at 10 points rather than 5. In the diagram below, the path shown is always moving horizontally or vertically. Are diagonal paths possible? And can you make a similar diagram for 3 processes and 3 resources? Number 4. A system has 2 processes and 3 identical resources. Each process needs a maximum of 2 resources. Is deadlock possible? And number 5. Can a system be in a state that is neither deadlocked nor safe? Explain. So these are all problems taken from your textbook. There are 5, technically 6 questions to answer here, and this is valued at 30 points of extra credit that goes towards your assignments. So this is your last assignment for the course, and after that, the real last assignment is going to be your final project. So we're going to implement one of the deadlock related algorithms as a computer program, and then we're going to try it out for ourselves. So if you notice that there's no, can you see where this, so, you may have noticed that every time I've assigned you one of your projects, it also included a problem from the textbook where it's, for example, is this deadlock, or is this, or what is the number of page faults this thing has, or can you draw the Gantt chart for this, or something like that. I'm going to do the same for your deadlock project, where I'm going to take one of the problems from the book, you're going to answer it by hand, and then you're going to answer it using the program you're going to write. So, that's going to be for next week. So, next week, I'll give you the instructions for your deadlock project. And that's going to be the end of the course. There's still a lot of OS-related topics that I did not get to cover because there's just so much. That's why we have a CSE-4600 and CSE-4610. Some of the things I had to cut out, but really wish I hadn't, are like security and protection. More about file systems. How does the disk, like under the hood, work? And by under the hood, I mean prop up the cover off of your hard disk drive and then void the warranty. Yeah, there's just so much more stuff. And we didn't even get to, like, what happens if we have a multi-core CPU? And, like, how do you even program a multi-core... How do you even write a program that can run on a multi-core CPU? We didn't even talk about distributed systems. I'm going to assume that your next instructor will cover all those topics, and even these past ones, in more detail than I have done here. But if you want a good idea of what is involved, distributed systems are when you have a computer that is basically made from multiple computers connected on a network. Security and protection, your computer system is full of resources and data that nefarious users want to get their hands on. They want to turn your computer into a zombie that would send out spam emails to everyone. Or they want to grab your credit card information. So we want security to make sure that doesn't happen. There's there are other means to protect yourself, such as two-factor authentication, which is probably, if you have any important emails and such, if you have any important accounts, it is a good idea to turn on two-factor authentication. Tom Scott has a really good video on that. So does Linus Tech Tips as well. What else is there? Oh yeah, I did not even get to talk about what happens when there's more about memory that I wish I could have talked about, such as something called trashing. Sometimes processes can take page frames from other processes, but if that goes too far, then processes are going to spend more time paging. And by paging, I mean sitting in the queue for the disk to get to load a missing page. If that happens, then the then the entire system will be spending more time on paging than it is executing code. That means the degree of multi-programming, that's the number of processes that can be run at the same time, it's gonna fall. Yeah, there's so much more things that we could talk about, but just isn't enough time for one semester's worth of time. So, whatever happens in CSE 4600, I hope I've given you a good idea of what to expect. So anyway, I'm going to end this discussion here, and yeah, this is gonna be your last set of slides. The next time we come back, it's going to be instructions for your Deadlock project. Okay? And with that, I'll see you next week for probably the last time, and we're gonna go from there. Alright? Have a good one. See you next week.